This video is brought to you by Squarespace. Get a new website up and running without having to write a single line of code. Just 2 days after the release of the first full-color images from the James Webb Space Telescope, the Webb team released all of their calibration data that was used during instrument commissioning. It's all available for download at the Mikulski Archive for Space Telescopes. Now, to be clear, these are the calibration images that were used to test particular modes of the instruments. They're not quite as nice and pretty as those used for the early release observations, and that's because those targets were chosen specifically so that they'd make beautiful images, and they were taken with at least 3 filters. That allowed a dedicated team to process those images and clean them up to make them ready for public release. On the other hand, calibration targets were chosen to test particular imaging or spectral modes of the individual instruments. But that didn't stop astronomers from downloading the data and doing their own image processing. One of them was Andras Gaspar of the University of Arizona. He put out this really cool thread on Twitter describing the MIRI instrument calibration images. Andras is actually a member of Team MIRI, and he was on console at the Space Telescope Science Institute in Baltimore, helping to get MIRI ready for science. Now, I've never commissioned a science instrument on board the James Webb Space Telescope, and I'm going to bet that you haven't either. So I thought it'd be cool to get together with Andras and let him tell us about what it was like to commission MIRI and describe the stories behind these images. Now, I should caution that my audio is a little less than perfect, but the good news is that Andras does most of the talking and his audio is just fine. So with that, let's learn about how MIRI was commissioned. Andras, thank you so much for joining me today. It's great to talk with you, and congratulations on setting up what I know it's jokingly referred to as literally the coolest instrument on board Webb, the mid-infrared instrument. But I was wondering, you're part of the Team MIRI, right? And can you tell me what Team MIRI means exactly?
Well, Team MIRI is a very large team and it's an international collaboration, right? We've got people from ESA, who were the main designers. Many parts for MIRI were from the US, and we've got a nice little team here at the U of A. And we've helped out from testing flight spares at JPL all the way to helping out now during commissioning.
What is commissioning like with MIRI?
Well, MIRI started its commissioning activities slightly later than all the other instruments, right? We had to cool down all the way to 7 Kelvin while the other instruments started working earlier. But we all got checked out early on. We turned on. We knew we were healthy. And then once the cooler got us down to our operating temperatures, we could start getting data.
When you saw those first images from MIRI, the very first ones, like we in the public got to see the alignment field, and all of the other instruments all had like really pretty spiky stars, and then MIRI had all this cool stuff in it, like all this gas and
That's
dust
right.
and stuff like that. What was that like seeing that for the first time? That must have been just a real thrill to see it for real, right?
Yeah, so we got those first images, I think on April 12th or 13th, somewhere around that time. And it was just an alignment field test on the Large Magellanic Cloud. And we downloaded images and they were beautiful. So we were already very happy. Most of those were taken at 7.7 microns, where those PAH features just light up. So that's what all of the other people got to see. One of the fields we also took image at 5.6 microns. These images came down on April 13th, and we got really excited and made the first color image. We were really happy, but immediately told to, all right, let's not share this with too many people. Yes, it's really, really pretty and we're happy, but let's just enjoy it ourselves.
Were you tempted? Like, did you want to, because you're pretty active on Twitter, did you just want to get out there and say, look at this? Look,
Oh, yeah.
Yeah.
Oh, yeah. I think, but not just me. I think everyone in all instrument teams were just ready to shout off the mountaintop just how amazing everything is working.
So this is like a really nice array of all of these parts of the LMC. What was going on here with all these different filters?
So this is an exciting image, and I think up to this point, this is the only area of the sky that has been imaged with all 9 MIRI filters. This image set was taken to define the flat field of the detector. Determining a flat field for MIRI is rather difficult because anywhere you look, you're going to see some background levels like this. So this observation was dubbed the 1,000 points of light method for determining a flat field. where a field was observed where many stars, but not too bright stars, were available. And this field was dithered around, and we would measure the brightness of the stars as they were dithered around the detector and see how they change. And this would allow a smooth, leveled out flat field to be determined.
So when you say that you dither, can you tell us what that means? Like you're moving the telescope just a little bit over and you're taking another picture. And what does that do for you exactly when you move the telescope around like that?
That's right. So dithering is exactly how you described. You move the telescope to place the same astrophysical object on different pixels. And there can be various reasons for doing this. Here we did this so that we could determine the flat field, obviously. But for other cases, you may want a mosaic. You may want to study the detector response because not all pixels are meant to be the same. Well, they're meant to be, but they're not. So there are many different reasons to dither around. And we do it with MIRI especially a lot.
Hi, I just wanted to let you know that you can download these images from Andras's GitHub repository in full resolution. And also I wanted to take a second to thank Squarespace for sponsoring today's video. Squarespace is designed to give you everything you need to get a new website up and running without ever having to write a single line of code. Simply choose from one of their many professionally designed templates and then use their suite of built-in tools to upload your content. I'm building a new website for our annual workshop for writers, and it's amazing just how easy and intuitive it is. With its new Fluid engine, I can move and resize elements and know they'll always line up with the overall layout of the site. You can add any type of content, whether it's photos, videos, newsletter signups, even entire e-commerce stores. Connect your social media accounts to display posts from your social profiles right on your website. Setting up a mailing list is a breeze. You start with an email template, apply your brand assets, and you're on your way. If you need a website done quickly and well, check out squarespace.com/launchpadastronomy for 10% off of your first purchase of a website or domain. You'll find that link in the description below. And now back to our chat with Andras.
So you took this image of the Cat's Eye Nebula, and it looks very familiar and also at the same time very different from the Hubble Space Telescope image. So tell me why you chose this particular target and what you were hoping to do with MIRI as part of the commissioning.
So these detectors have a certain property where if you place a bright object on it, even after you remove the bright object, it's going to leave a little ghost behind. Just like some LCD screens burn in, after a while, not the same process happens, but you still have a latent image on the detector. So we had two different programs to test the detector's response to bright objects. This one, taken of the Cat's Eye Nebula, while super pretty, the primary goal was not to study the cat's eye and see how nice it looks, but to see how much time after taking this image does the latent image sort of decay down on its own. It takes about half an hour-ish for it to sort of disappear.
So does that mean that every time you take an image of a bright target with MIRI, you have to wait 30 minutes before you could take another bright image?
So that's a really good question. So this is one of the reasons why we do dithering. If you take, most bright objects will not be extended this much. And if you dither it around, you can sort of guarantee that you don't place really bright sources on the same region again. So you can combine those dithered observations into a nice looking image. But this is sort of a problem for these types of detectors. And the only solution that we really have is what's called annealing, where we take the detector and we heat it back up. So the operating temperature for MIRI is around 7 Kelvin, and it gets heated up to 20 Kelvin temperature, cooled back down to 7 Kelvin. And during this process, the latent images are remedied and they're gone.
It's hard to think about 20 degrees above absolute zero as being warm, but that really is, yeah, but that's hot for MIRI. Yeah, that's so counterintuitive.
That's right.
What then might be the risk of this procedure? Is there any chance that the cooler might fail and not be able to bring MIRI back to its operational temperature?
As far as I know, the cooler doesn't change. It's an internal electronics that actually heat up MIRI. So
that's really cool. This is rather pretty.
It should be familiar. It's the original PR image, just in color.
And we're also seeing a little bit more of the detector, aren't we?
That's right. So the small upper field is filled up, as you can see. So that's a part of the detector where we have the 23 micron Leo chronographic area, but that area it can still be used for regular imaging because the Leo chronograph is basically just a little mask in there that blocks the stellar light if you put the star behind it. All around that area, you can still image. So we can use it to take images.
Oh, wow. So is that mask present? We're just not seeing its effect because it's not sitting on top of a star?
Well, and this is a combined image. It's dithered around. So that gap was filled up by the dithering.
That's really, really cool. So tell me about what's going on with this beautiful image of a Seyfert Galaxy.
So this is at 5.6 microns also. And you can see the cross artifact jumping out at the nucleus there. This was taken for an annealing test, the same as we've talked about before, bright image. But I think this was the one where we actually annealed, and the other one we just looked how it disappeared. After this one was taken, an annealing was done to see if it gets rid of the latent images.
Obviously, what really jumps out is just how bright that nucleus is. So this is a really active nucleus. Is that correct?
That's right. That's right. It's a Seyfert Galaxy, so they have active nuclei. Only a small percentage of galaxies are like this. And right, the Seyferts are different from quasars in the fact that you can actually spatially resolve the galaxies around the nucleus.
They're not as active as a quasar used to be, but they're still pretty active. And it doesn't really come across in the Hubble image, which I realized was not taken to show off the nucleus per se. It was taken to resolve the rest of the galaxy. But you just look at this thing with MIRI, and that nucleus just jumps right out at you.
Yeah, the accretion disk is quite bright at 5.6 micron.
That's amazing. And then looks like you turn to point to the galactic center.
3 degrees offset from the galactic center, but close enough that you can see all the molecular clouds near.
This is a stray light pointed model correlation. What does that mean exactly?
So during this observation set, this was not just the single image taken. So a really high background one was taken here near the galactic center, and they just wanted to measure how different background lights actually enter.
So what is next for MIRI? I mean, or I should say, what is next for Team MIRI? You have such a great group of people there, and what are you all going to do? Are you all going to be like, well, bye, we got MIRI commissioned, and now we're going to go off and do our own things, or are you still working together?
It's a fantastic group, and yes, many people from the European consortium have traveled back home already, but ESA has quite a few people who are stationed at Space Telescope and are going to continue to work on the project.
Andras, thank you so much. This is just amazing learning about MIRI and learning about what it was like to go through the commissioning process, and just congratulations to you and the whole MIRI team for just bringing us this incredibly amazing instrument. And really just, this is what's taking Webb really deep into the infrared as far as we can see. It's just amazing work, and thank you.
Oh, thank you so much for talking with me. And I'm really happy to share, because I don't think many people understand why we needed 6 months necessarily to get the telescope up and running, but we needed to understand how everything works.
It's a complex machine. Thanks.
It is.
Yeah.
Thank you very much.
Thank you, Andras Gaspar, for telling us about commissioning MIRI, and a huge thanks to my Patreons for helping to keep Launchpad Astronomy going, and I'd like to welcome John Roberts as my newest supporter. And if you'd like to join me on this journey through this incredible universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay curious, my friend.